Have you ever wanted to minimize something in your life? Or how about maximizing something? Maybe you want to minimize the amount of junk food you eat. Or how about maximizing the hours you sleep in your busy week? The process of wanting to minimize or maximize is called optimization. In differential calculus, we need a model that is differentiable, and we're hoping to seek that absolute min or that absolute max that will give you the answer to your optimization problem. This leads us to further our usage of the first derivative test and the second derivative test. So our objectives in optimization is to use problem-solving skills to create such a differentiable function. Then, of course, use the first or the second derivative test to optimize that function and write a conclusion to the scenario. The first theorem is the theorem that I use the most when it comes to optimization. This is also known as the first derivative test, and you've seen a variation of this before. The only difference is now we are actually going to seek the absolute maximum, or we're going to seek the absolute minimum by studying whether or not the first derivative is positive or if the first derivative is negative around a critical number c. The second derivative test is an optional test that you could use to determine whether or not you have a local min or local max. In either case, what you're wishing for is exactly one critical number. If you have exactly one critical number, then it's much easier to conclude whether or not you have an absolute min or an absolute max. Now here's the general strategy for optimization problems. You want to read and extract information. This might take a while. You might need to read the problem several times. And throughout the problem-solving process, you might go back and read the problem again. You want to ask yourself, what is the unknown? What are the given quantities and conditions? What are you trying to optimize? Are you trying to minimize? Are you trying to maximize? Write information under two categories. One category is called constraints, and the other category is the objective. Under constraints are usually diagrams that you could draw or domain restrictions that you can indicate. On the objective side, you really want to state, are you minimizing or are you maximizing, and be very specific. You might even want to remind yourself of the units that are being measured. The third step is really the key to all these problems. You want to write a function that you want to optimize in terms of one variable. And this requires a little bit of problem solving. It might require a lot of algebra. It might require some geometry, some trigonometry, but you're basically going to use all your prior math experience to try to figure out what this function is going to look like. Once you get your differential function, you're going to use the first derivative test or the second derivative test to see if you have an absolute min or absolute max at a critical number. Now the goal is to get one critical number. A lot of times if you have more than one critical number, then I would advise you to use the second derivative test. But if you only have one critical number, then the first derivative test is a little bit easier to use. Lastly, in your last step of your general strategy, you want to write your conclusion about your optimization in a complete sentence and ask yourself, does the answer make sense? Is it realistic? Why don't we dive into an example to see the strategy in action? Suppose you run a small business and you plan to create storage boxes for shelves with a square base and an open top. The box must have a volume of 32,000 cubic centimeters. find the dimensions of the box that minimize the amount of material used. Like I said, what I like to do with these problems is to separate two categories of information. First category are called constraints. And constraints are basically limitations in what you want to optimize. The second category is the optimization objective. And I usually use an entire sheet of paper for one optimization scenario. You might even need two pieces of paper, and I usually just split the paper down into two columns, where one column is indicating constraints and the other column involves the objective. Now, the objective is often stated in the question or stated in the direction. We want to minimize the amount of material used. In other words, we want to minimize the surface area of this box. And we could even remind ourselves, what is the measurement for surface area? It will be square centimeters. Now, what are our constraints? Our constraints is actually volume. The volume is set, it is fixed. And the other thing is constraints allows us to draw a picture. Sometimes the picture can really help us indicate more constraints. If I had to draw a box with a square base, maybe it'll look like that. And it's got to be a box. I could draw some height. It's a little higher. And so there's an upright box there with a square base. If I label the square base, that means another constraint is x is greater than 0. And the box has some height, and we know that the height is greater than 0. We could find the volume of a box simply by looking at length times width times height. So we know x times x, which is x squared, times height, has to equal 32,000. Now, I'm going to go back to my objective. We want to minimize the surface area. Once we have a picture, we could cross over to the objective side and write an equation for the surface area. So the surface area, I will use capital S to symbolize surface area, is equal to x squared plus 4 times x times h, which is the area of the lateral sides. The x squared is just the area of the base, and remember this has an open top. The issue is that we have the surface area in terms of two variables. But one of our general strategies is to actually write the surface area in terms of one variable. The way we usually do that is look at our constraints. See if there's a relationship under our constraints that allows for a substitution. And I believe there is. We know x is non-zero. We could solve for h. And we take this h and put it over towards the objective side. Now we're able to write a differentiable function in terms of one variable. Simplify this function. And now we're ready to optimize. In order to optimize this function, we need the first derivative. Continue with function notation. And we'll go ahead and find common denominator here. And we want our first derivative in factored form. That is the difference of two cubes. Factors rather nicely. You just need to know your difference of two cubes formula. Now we're ready to find critical numbers. And we already know x cannot be 0. So there are no type 2 critical numbers here. We're only going to look for a type 1 critical number. So remember, for a type 1 critical number, we simply set the first derivative to be 0, and we need to find when the c value will yield the output of 0. There are three factors that multiply to get you 0. Two of them cannot be 0. Remember that the 2 can't be a 0, and this factor here cannot be 0, because in your formula for the difference of two cubes, this here is always greater than 0. So the only thing left to solve for is this last factor here, c minus 40 is equal to 0. That means our critical number, and our only critical number, is actually 40 centimeters. Now, what did we do before with our critical numbers? We test them on a number line. So I'm going to draw a number line. And I need to test this in the first derivative. Our first derivative in factored form. I could use this one here. So why don't we test the first derivative evaluated at 1. That is clearly going to be negative. And let's look at the first derivative evaluated at 50. That's clearly going to be positive. So we know our surface area function is decreasing, and then the surface area function will increase after our critical number. So if it decreases before our critical number and increases after our critical number, that means we have to have a absolute min. And the reason why it's absolute is because we only have one critical number. So that actually will yield the lowest value for our surface area function. So we are able to conclude that we have minimal surface area. Now we got to answer the question. We want to find the dimensions of this box. So we know we have 40 centimeters along its base, 40 centimeters here, 40 centimeters here, but we need to find h. So how do we get h? And so I'm going to go back in a circle here. I shouldn't say I go back in a circle, but I'm going to cross over to the constraint side and help us find our h. So the difficulty of solving puzzles like this is trying to stay organized. Do your best in staying organized, and then you're going to realize h here is going to be 20 centimeters, and we're ready to answer the question. For a box of volume 32,000 cubic centimeters, and minimal amount of material used, the dimensions of the box should be 20. Oh, I take that back. Meant to say 40 centimeters by 40 centimeters, and then finally by 20 centimeters. And does this answer make sense? Absolutely. Now going back to this, notice it's very hard to keep track of what you do first. And there are times where I actually have to jump back between the constraints and then jump back to the objective. Then sometimes I go to the objective and I jump back to the constraints. Just a recap of the summary here, I could go back and label which steps I actually did first. So usually I start with constraints, but then I quickly go back to the objective. Then after I do a little bit of the objectives, I later realized I need to get h in terms of x. And that gets us to this fourth crucial step right here, which is finding that differentiable function in terms of one variable. Then we look for critical numbers. Turns out we have exactly one, which is what we want. So this was our fifth procedure right there. Our sixth procedure is actually apply that first derivative test to see if we actually have an absolute min. Okay, we have an absolute min for our surface area. And then our seventh procedure is over here. And our eighth procedure is actually writing that conclusion and asking yourself, does this make sense? Were we able to optimize in this particular scenario?